Hey, how's it going? It's Dr. Powers. Today we're going to look at another application of the chain rule and implicit differentiation, handling problems where there are related rates. And so these are really best illustrated with some examples, so we're going to just dive right into it. Okay, here's an example. We're pumping air into a spherical balloon at a rate of 100 cubic centimeters per second. All right, it's a constant rate of increase. Now, how fast is its radius increasing when the diameter is 50 centimeters? So as you can imagine, at the beginning of this inflation, the radius is increasing fast, and then the radius is going to slow down its increase as the volume gets bigger, right? Well, what we do is we find the equation that relates the radius and the volume, right? The volume is 4/3 pi r cubed. This is the formula for the volume of a sphere. And now I think it's worth noting that when the diameter is 50 centimeters, that means the radius is 25 centimeters. So we'll just keep that in the back of our minds. And so what we're going to do is we're going to take the derivative of the volume with respect to time. We're going to do an implicit differentiation. And so we'll get v prime equals, let's see, we have 4/3 pi times power rule 3r squared r prime. And so what we're looking for is to, we can cancel these 3's, and what we're trying to find is when we have the v prime, the volume is increasing at a rate of 100 cubic centimeters per second. So we can plug that in, 100 for the rate of the volume increasing. 100 is 4 pi times 25 squared times r prime. So we could we can actually simplify this a little bit. 25 times 4 is 100. We can actually get 1 equals pi, we can write 1 equals 25 pi r prime, and so solve this. R prime equals 1 over 25 pi, and that's going to be centimeters per second. So this is the rate at which the radius increasing. This is when the radius is equal to 25 centimeters. Okay, let's take this example. We have a ladder that's 10 feet long. It's resting against a vertical wall. So I'm going to just start with a little diagram. The ladder is 10 feet long, okay, and then it's resting against that vertical wall. The bottom is sliding away at a rate of 1 foot per second, okay? And that means, of course, that the top part is going to be sliding down. We want to know when the bottom is 6 feet away, how far is the top sliding down? So I'm going to let x be the distance, all right? So we have, we can, for any value of x, we know the value of y, right? We have this, I'll put it as y. Y squared plus x squared is equal to 10 squared. That's the Pythagorean theorem. And we have dx over dt is going to be 1. That's to say that x is increasing at 1 foot per second. And so what we're going to do is take this, we're going to take the implicit, like the derivative with respect to t, treating y as implicitly as a function of t, and we're going to solve when x equals 6, we're going to find what is the derivative of y. So we're going to have 2y, and I'll put dy dt plus 2x dx dt equals 0, because the derivative of the right-hand side is 0 because it's constant. So I'm going to plug in the missing pieces. We have, we actually know when x is 6, we're going to have the triangle that is a 6, 10, and if you work this out, this is a special triangle. This is indeed going to be 8 feet on there, on this side, right? Because if you solve y squared equals 36, y squared plus 36, that's 6 squared, equals 100. Y squared is 64. It's 8. So we have 2 times 8 times dy dt, which is what we're trying to find. We don't know that. Plus 2 times 6 times 1 equals 0. In other words, we have 16 dy dt equals negative 12. So dy dt is going to be negative 12 over 16, which could be written as negative 3 over 4. And that's going to be in feet per second at this moment in time. Okay, so now we have this other example. A water tank is an inverted circular cone, which is to say it looks like this, like a snow cone. And the base radius, this is from here, the base is actually the circular part, has a radius of 2 meters, whereas the height of this thing is 4 meters from top to bottom. Okay. The water flows into the tank at a rate of 2 cubic meters per minute. We want to know how fast is the water level rising. How fast is that water level rising when the water is 3 meters deep? So, first off, what is the formula for a cone? A cone is the volume of the cone 1/3 height times pi r squared. This is the volume of just any sized cone. Now, actually, we don't so much care about this. What we realize here is the relationship between this height and the radius, in that any smaller cone is going to be proportional to this. So this is a cone in which the radius is 1/2 of the height for this cone. So what I'm actually going to write here for this cone, for this tank, for any amount of water which has a height of h, the volume is going to be 1/3 h times pi and h over 2 squared. The radius is 1/2 the height. So I'm going to simplify that to be, that's the 2 squared is a 4, that's pi over 12 h to the 3rd. Now, that's the important thing to have here. This is the relationship. Now, I'm going to now take the derivative with respect to time. So that's going to be dv dt equals pi over 12 times 3h squared dh dt. Now we're talking about how the height of this water cone, not the full thing, but the water cone. That's the h. And now the volume is increasing at a constant rate of 2 cubic meters per minute. That's the 3 is going to cancel there, so we'll have pi over 4, and then we have at what time. We are asked when the water is 3 meters deep, so h is actually going to be 3, and then this is what we're solving for, dt. So we can, if we solve this, we have dh dt is going to be 2 times 4 over pi times 1 over 9. We get everything on the same side. So what we're going to get, we have 8 over 9 pi. That's going to be in meters per minute. I don't really fit it there. 8 over 9 pi meters per minute. So at the moment when the water is 3 meters deep, that's how fast the height of the water is rising. But that changes as the volume increases, right? You can see that it takes more water to rise up a meter at that point than at the beginning of the filling process. So in general, when you're faced with a related rates type problem, these are the steps that you can use in order to solve it. First thing you want to do is be sure that you read carefully everything in the problem so that you're not confusing two different concepts or we're like mixing up the rates or something like that. You want to make sure that you're reading it carefully so you'll understand what's going on. Second, it's really good to draw a diagram because usually these are going to be physical processes. You can see how the different components relate to each other physically, visually. That is going to help you realize what formulas are going to be useful in this situation. Next, you want to introduce notation, which is to say you want to assign a variable name or symbol to anything that is going to be some function of time. Because in all of these cases, everything's going to be a function of time. Time is happening. This is the rate. It's a rate over time. So anything that's going to, you want to define the notation that you're going to use for those quantities that change over time. Next, you want to express the given information and the required rate, the thing that you're looking for in terms of derivatives, in terms of some d something over dt. Next thing you want to do is write an equation relating the quantities. It might be a geometric formula. It might be something else that's known, but some equation that relates the different quantities that you've assigned variable like letter names to. Next thing you want to do, use the chain rule to differentiate both sides of the equation with respect to t. And the last thing you do, you substitute in the given information that you have and solve for the required rate. We'll take a look at a couple other examples and you'll see what I mean. Okay, we have in this example, we have got two cars traveling towards an intersection. A is traveling west at 50 miles per hour. B is traveling north at 60 miles per hour. Now, we want to know at what rate are the cars approaching each other, which is to say, at what rate is the distance between the two cars changing when A is 0.3 miles and B is 0.4 miles from the intersection. So A is traveling west. So what I want to do is I'm going to show let's say this is like the point where car A is. And on this axis we have car B. Now what we're interested when A is moving in this direction at 50 miles per hour, B is going up at 60 miles per hour, and we're interested at the point when they're 0.4 and 0.3 miles away from each other. We're going to, let's just move this. We're interested in the distance between the two cars. Now, we're going to let's have x. So x will be the distance between A and the intersection, and y is going to be the distance between car B and the intersection. All right, and so we have dx dt is given as this is changing at a rate of negative 50 miles per hour, which is to say this distance is shrinking down. Dy dt is also decreasing at a rate of negative 60. Okay, and then the distance between them, d, is the square root of x squared plus y squared. All right, it's a right triangle. So this is now we're trying to find. We want to find the derivative of d with respect to t. This is what we're asking for when x equals 0.3 and y equals 0.4. So this is how the setup goes. We'll now take the derivative. dd over dt is going to be, we have to use the chain rule, right? And remember, when you have the derivative of a square root of something, it's 1 over 2 times that square root of the x squared plus y squared. And we have to multiply this by the derivative of this inner thing, which is going to be 2x dx dt plus 2y dy dt. And so I'm going to, now it's just a matter of, I can just plug everything into this. And so we're going to have, the numerator is going to be 2 times 0.3 times negative 50 plus 2 times 0.4 times negative 60. The denominator is 2 times the square root of 0.3 squared plus 0.4 squared. And we just can work that whole thing out. You're going to get negative 78 miles per hour, which is to say that's the rate at which the distance between the cars is decreasing at that moment in time. Okay, so we have a man. He's walking along a straight path, 4 feet per second, constant rate of constant speed. A light is located 20 feet from the path and focuses on him as he walks. We want to know at what rate is the light rotating when the man is 15 feet from the point on the path closest to the light. So here's a picture of what this could look like. So I'm going to put the spotlight here and say this is where the man is. He's going at that rate at 4 feet per second. And this is a 20, that's 20 feet from here, and this is shining straight at him, right? Now we're interested at when he's 15 feet from this point, we're interested in let's think of it in terms of the angle theta, right? So we want d theta dt when, let's see, let's have the distance here, let's have that be x when x equals 15. Now since he's moving to the right, we have dx dt is negative 4 because he's moving to the left. Did I say right? He's moving to the left. So that x value that's decreasing. Now we need to figure out the math involved here. In fact, this could be found using some trigonometry, of course. Now the angle that this spotlight makes with the axis is going to be found using a tangent. Let's write this. I'm going to put this right triangle over here. We have 20. We have 15. So this is a constant 20. We have this is going to be x. So we have the tangent of theta is going to be, remember it's the vertical over the horizontal. That's going to be 20 over x. All right. So 20 over x, that's the tangent of theta. So what we're going to do now is we're going to take this and we're going to take the derivative with respect to time. So remember, the derivative of a tangent is the secant squared of theta, and the chain rule says we get a d theta dt coming out of that. On the other side, we're going to take the derivative of 20 over x, which is, remember, this is 20x to the negative 1. So it's going to be negative 20 over x squared. That's going to be x to the negative 2 times dx dt. Now, plugging everything in, we actually need to figure out what is that angle going to be. When x is equal to 15, theta is going to be the inverse tangent of 20 over 15. That's 15.13 degrees. And so let's put all this stuff into our equation now. We have the secant squared of 53.13 degrees times d theta dt is negative 20 over, what do we have, 15 squared, and then the dx dt, remember, that's negative 4. So that's everything. Solve this and you get d theta over dt is equal to, you get 0.128 radians per second, or if you wanted that in degrees, that's 7.33 degrees per second. Those are the examples we'll do now. Of course, we'll get more practice, and you'll get better and better at this. It really just comes to practice. But these are the same real steps that you can kind of use for every one of these problems. Yeah, well, we'll just see where we go from here. Okay, bye.